brings us to our design recommendation. My name's Nico Stewart, by the way. We decided to combine the phase change material vest with a high pressure air system that will use an external tank. The phase change material vest will have internal pouches that will be able to house removable phase change material packs, and the vest will also be fitted with air tubes that will be positioned throughout the vest so that high pressure air can flow to the inside of the suit and provide that cooling, the evaporation and convection. The tubes in the suit will be connected to a quick connect valve that will be located in a position on the suit that is easily concealable and also easily accessible. That way, when Sparty decides he needs a quick burst of cold air, he can connect to the external tank very quickly and very easily. We will position the external tank probably in the tunnel of the stadium or wrestling center, somewhere off the court or off the field where Sparty can easily access it, go for 30 seconds to a minute of air for quick relief. And also during Sparty's longer breaks, the phase change material can be replaced because that's part of our testing. We don't know how long each of these packs will last for, and so we expect to have frozen packs ready, available, so that we can substitute them for the melted packs during halftime or so. And that leads us to our next project area, where we will create a freezing box for the extra material.
My name is Ahmed Zahid. We're going to build the freezing box. The main idea of the freezing box, like my partner said, is to make the phase change material be usable at any time needed. And we'll make it portable, so it's functional whenever needed. And we needed to make a temperature range between 0 and 25, so the person who's wearing the vest won't freeze. We're gonna build it using a cooling box, so even if the system stopped working, it will maintain the temperature that we need. Also, we're gonna use a power source that change from AC to DC, an output of 15 volt and 3 ampere. And a voltaire junction of 60 watt. The 60 watt voltaire junction, usually the temperature range is between, for the hot side is 50 Celsius and the cold side is less than 5 Celsius degree, which is reaching around 5 seconds or less than 5 seconds. If we left the hot side of the voltaire junction hot forever, the hot side is dominant, so the whole voltaire junction will turn out to be hot. That's why we're going to use a heat sink to cool down the hot side of the voltaire junction, and we're going to plug it like this over here, where the heat sink is going to transfer the temperature of the voltaire to itself. Then we're going to plug a fan to it to transfer it to the. We're also going to put the same heat sink on the cold side, and then to inside the box. And also we're going to put the temperature sensor on the system, and we only need 3 elements, which is power transistor and potentiometer and temperature sensor. This is a quick graph of how we're going to plug the whole thing. The load is only the fan and voltaire junction, which is going to be almost as big as 2 fingers like this.
So moving forward, we intend to evaluate the different phase change materials that we have collected. We have 4 samples right now, and they each have different melting temperatures. The silver pack that you saw going around has a melting temperature of 80 degrees Fahrenheit. The 2 white packs melt at about 56 to 58 degrees Fahrenheit, and that blue one melts at 32. So we need to evaluate the melting temperature, see how they actually feel against the skin, and try and verify our theoretical predictions. So we intend to do that by doing some physical testing, and you can also see that the sizes of the packs vary quite a bit, and also the weight. And so we need to make sure that they physically fit underneath the suit, and we have a mock-up that we will use to exercise in and actually get some data. And also we need to determine the optimal airflow rate for the high-pressure air system, the optimal tube diameter, and the best positioning of the tubes within the vest to give the best cooling. And these are, in case you didn't see the phase changer materials, here are the pictures of them with a 6-inch ruler for scaling purposes. But I think everyone got a chance to hold on to one of the packs.
Here's our first diagram. So the main idea is, like we all discussed here, we want to maintain the mobility and isolate any noise coming out of the mascot. Also, we want to eliminate the sweat from the person who's wearing the mascot by the tubes. And to make it usable at any time, we'll use the freezing box. Any questions?
The PCM, the 400 kilojoules of heat absorption, is that number maintained, or does it decrease over time the longer that you wear the costume?
The 400 kilojoules is the total heat that it can absorb going from the frozen state to the liquid state. So kilojoules is the total energy, not a power of absorption. Yes?
So the high pressure air system, would that be on the sidelines and then you would connect to that every 7 minutes or something? So, okay. So only the phase change material would be going with them all the time?
Mm-hmm.
Okay.
So the 15-pound limit you came up with, that seemed kind of arbitrary. How'd you determine that?
It was
It's
kind of
kinda
arbitrary.
arbitrary.
It was a design target that we came up with, something that we felt that Sparty could carry without too much problem.
We also consulted our project sponsors to see kind of how much weight, but again, it has to be distributed on the system. We wouldn't want to have 15 pounds on one side, yeah.
And the other question I had is, the tubing material for the air pressure system. What type of, you need a material that'll have a high heat transfer.
But-
So,
No, the air will be directly inserted into the suit. The air won't just be flowing through the tubes. The air will be just injected into the suit, and then it'll flow out through, the holes around the neck and the holes around the arm, so that we can actually get evaporation that
so
way.
you have chambers inside there that would conduct the air to certain ports that would just let it out.
Exactly, exactly.
Okay, I kind of misunderstood it. All right. Okay, good, thank you.
Thank you.